Dear students, this is a lecture session for the course on nanoelectronics, 5th module of 8th semester students of Kerala Technological University. I am Professor Kerivendran taking the class session here. The 5th module deals with the transport of electrons in the 2D electron system under the effect of electrical and magnetic field. Transport of electrons in quantum heterostructures under the action of electric field. We know that quantum wells are formed at the interfaces of semiconductors of different gaps, that is heterostructures. In the quantum well, how the transport of electrons are taking place is our subject of study today. As you know, in heterostructures or quantum wells, there are two types of transports of electrons possible. They are the parallel transport and the perpendicular transport. Then what is parallel transport? In low-dimensional 2D quantum heterostructures, conduction band electrons in the quantum well behave almost as free carriers for their motion along planes parallel to the interfaces of the well. And this kind of transport is called the parallel transport. It means that the motion of electrons will be on a plane parallel to the interface of the potential barrier. The parallel transport in nanostructures was investigated first in the case of MOSFET structures, and that actually led to the invention of MOSFET. The electron motion in these devices take place in a region free of charged dopants, and therefore electrons can attain very high mobilities, or devices with this kind of 2D structures will be having very high speed of operation. Electron scattering mechanism in parallel transport. In the transport of electrons in 2D structures, there are different electron scatterings possible. The main scattering mechanisms in semiconductor nanostructures are electron phonon scattering, impurity scattering, surface roughness scattering, inter-subband scattering. Now, what is electron phonon scattering? The quantum of a lattice vibration is usually called the phonon. Electron-phonon interaction is commonly observed in most of the materials, especially in bulk materials. At room temperature, the lattice of the material is not static, and the atoms vibrate about their mean position. The electrons will have a chance to make collisions with the vibrating lattice under their motion, and such collision is usually called electron-phonon collision or scattering. The vibration of the lattice increases with temperature. The phonon scatter mechanism is very predominant at a temperature more than 15 Kelvin. In low-dimensional nanostructures, such as 2D quantum wells, the electron phonon scattering is very predominant as the well width is very small. The well width is the A, usually we designate it as A, and that is very small. In a 2D quantum well, uncertainty in the perpendicular conduct of the momentum should be greater than or equal to h by A, where h is the Planck's constant and A is the thickness of the well. In the case of bulk semiconductors, where the acoustic phonons are more predominant and they are conserved in the momentum, Whereas in electron phonon scattering, since the width of the quantum well is very narrow, the phonon momentum cannot be conserved. In semiconductors, the electron phonon scattering results a decrease in mobility of charge carriers involved. Next is the impurity scattering. The scattering in low-dimensional semiconductors is mainly due to the impurity due to ionized or neutral impurity scattering at low temperatures. The main difference between scattering phenomena in bulk semiconductor or in a 2D system for a parallel transport is that the location of symmetries are often separated from 2D plane in which the electron move. For example, in modulation doped heterostructures, the charged donors are located in the aluminum gallium arsenide, while electron movement takes place in a separate region, that is in the gallium arsenide parallel to the interface. Similarly, in a MOS structure, electrons move within the inversion channel, and that is separated from impurities located in the thin gate oxide. For the calculation of impurity scattering in MOSFET quantum heterostructures, usually some simplifying assumptions are made, and for example, delta doping. The ionized impurities are supposed to be located in a 2D plane at a distance of d of the electron channel, and that the electrons in the channel which participate in the scattering events are those with energies very close to the Fermi levels parallel to the interface. It is also assumed that the concentration of impurities is not too high, so that each charged impurity interacts independently with the carriers. With these assumptions, we can conclude that the mobility of the carriers increases cubic times. That is, it varies as d cube. But there is an optimum value for this d. That is, d is the thickness of the quantum well plus the thickness of the barrier. If d is too large, the concentration of electrons in the channel diminishes significantly. As a consequence of the decrease in electric field and the transconductance of MOSFET is greatly reduced. It means that the impurity scattering reduces the mobility of electrons in the channel. You know, as the transconductance of the channel is reduced means the conductivity is reduced. It means that the resistivity of the channel increases. That ultimately causes to reduce the mobility of the electrons. Surface roughness scattering. Surface roughness scattering is sometimes called interface scattering, and that's mainly due to the interaction of electrons with roughened surface, in contrast to the ideal perfect flat surface where the interaction would be elastic in nature. The interface scattering for parallel transport in modulation doped heterostructures is not that important because high perfection of interface are possible with modulation doped heterostructures as their interfaces are grown with molecular beam epitaxy. But in the case of MOS structures, where the interface scattering becomes very predominant, since the oxide is grown thermally and the interface is not as perfect as in the case of modulation of the heterostructures. The interface scattering in MOS structures depends on the width of the quantum well, because as the width decreases, the electron wave function penetrates deeper into the oxide semiconductor potential barriers, and the electrons are more exposed to the interface roughness, and its corresponding scattering increases. This is the reason for decreasing the mobility of electrons in MOS channel when the gate voltage is increased. Next is the inter-subband scattering. Inter-subband scattering is mainly due to the transition of electrons in a subband or between two subbands. Let us consider the case of a 2D system confined in a potential well. For large electron concentration in the well, the levels with the energies higher than the first level, that is energy E1, will start to become filled. Now suppose the electron concentration is very high, so that the Fermi level EF just crosses the quantity level corresponding to level n is equal to 2. Then electrons with energies around EF, that is Fermi level energy, can either undergo an intraband scattering transition within the subband n is equal to 2 or an inter-subband transition between subbands with level n is equal to 1 and level n is equal to 2. As a consequence, the electron mobility should become smaller. Otherwise, as the electron concentration in a quantum well increases, additional scattering channel starts to contribute to the overall scattering rate, and that causes the mobility of the 2D electron gas to get decreased. When the temperature approaches about 100 Kelvin, that is almost at the room temperature, the dominant scattering mechanisms are mainly due to phonons. The temperature dependence of mobility of electrons in a silicon MOSFET is shown in the figure. The mobility of electrons in a silicon MOSFET is much lower than that in the case of a MOSFET. There are several reasons for this. See the temperature dependence of electron mobility in silicon. This axis is the electron mobility axis, and this is the temperature axis. Almost at room temperature of about 100 Kelvin, see the electron mobility get decreased, and channel electron transport will be getting decreased when the temperature reaches almost at a room temperature 100 Kelvin. Moreover, in the case of silicon MOSFETs, the effective mass of electron for silicon is much higher than that in the case of gallium arsenide. The effect of impurity scattering in a silicon MOSFET caused by charges and impurities in the oxide and interface is larger than in the case of aluminum gallium arsenide structure. The silicon oxide interface is usually manufactured or fabricated, or it is grown thermally, and it is not as perfect as aluminum gallium arsenide interface, and hence surface roughness scattering is higher at low temperature. With this, we conclude this session here. The next class, we will see the hot electrons and the transport of hot electrons in parallel transport.